Okay, so thank you, Tom, for the invitation. I'm learning a lot here, lots of very interesting talks. So this is work which has been done over almost 10 years now. Together started with Christian Frank, with Govan Menon, and later on with Sheehan, and then mostly more recently with Tom. So as I say, we started in about 2012. We initiated a statistical study of the performance of various standard algorithms to compute the eigenvalues of random real symmetric matrices. In each case, the initial matrix is diagonalized either by a sequence of isospectral iterates or by an isospectral flow. So in the discrete case, as k goes to infinity, then generically HK converges to a diagonal matrix. So what that means is, given any epsilon bigger than 0, it follows that for some first time k, the off-diagonal entries of HK are of order epsilon, and hence the diagonal entries of HK give the eigenvalues of the original matrix H0 to order epsilon. It's a similar situation for continuous algorithms. So the prototype of the discrete case is the QQR algorithm, which I'm not going to describe it again, just describe it. Here it is with, sorry. What? Sorry. Did you? Okay. Okay, so this is without shifts. I could look at the shift case, but let me just focus on it without shifts. And an example of the continuous algorithm is the Toda flow, which is dH by dt is the common case of H. B of H is the lower triangular part of the matrix anti-symmetrized. Both of these are completely integrable Hamiltonian flows, a fact which we'll return later. So the main finding is the following. And this is, if you want a takeaway from this talk, I'll give some more takeaways later on. It is this: the fluctuations in the stopping times were universal. So what do I mean? So, and they were universal independent of the ensemble considered for the matrices H, whose eigenvalues we're trying to find. So more precise, if I have n by n real symmetric matrices H, chosen from some ensemble E from a very wide range of ensembles, and for a given algorithm A and the desired accuracy E, then TH, H is your matrix, chosen from the ensemble, epsilon is the accuracy, n is the size of the matrices, A is the algorithm you're using, and E is the ensemble from which H is chosen, and this T is the stopping time for the algorithm A applied to the n by n matrix H chosen from the ensemble to achieve an accuracy epsilon. So what you do is you're going to choose maybe 5,000 to 15,000, 20,000 matrices H from your ensemble E. And for each of these H's, you run it until you achieve your accuracy epsilon. You do that 5 to 15,000 times, and you compute the sample average, and you divide by the sample variance, and you compute this histogram. And this is the result, is that for a given algorithm A, and for epsilon n in a suitable scaling region, you should think of this in sort of as a physicist would, or like your scaling region is like a pressure temperature diagram. If you're in the right part of your phase space, then you'll observe this phenomenon. Then the histogram T tilde will be independent of the ensemble. That's the phenomenon. Now, in general, the histogram will depend on A, but for a given A and epsilon and n in the scaling region, the histogram will be independent of E. such two-component universality, two components, right? There's the average and the standard deviation, or the standard variance, is analogous to the classical simple central limit theorem. Again, if you know the mean, you know the standard deviation, this will converge to standard Gaussian. So it's in some sense a generalized version of the classical central limit theorem. So here's an example. On the left-hand side is the QR algorithm. As I say, if I wanted to use shifts, I would get a different histogram. But here you see there are two different histograms, one on top of the other. One is for when you choose your matrices from GOE. The other is from choosing them as Bernoulli matrices plus or minus 1. And your accuracy is 10 to the minus 10, and n is 100. And you see that the two histograms are lying one on top of the other. On the left-hand side is for QQR. On the right-hand side is similar data, but now for the TODA algorithm. The thing I would ask you to notice is that these are really different. So the histogram depends on the algorithm, but does not depend on the ensemble. Now, this particular case, our stopping time was dictated by deflation. So you take a matrix H, you break it into block form, and you run it until the off-diagonal entry blocks are of size less than epsilon. That means that if I just discard the off-diagonal pieces, the eigenvalues of this matrix give me the eigenvalues of the original matrix to order epsilon, and then you repeat the algorithm again and again until you achieve your desired accuracy. But obviously, your algorithm is going to depend on your stopping time. Different stopping times give you different algorithms, and I'll speak about more of that later. Now, so far, we were just looking at eigenvalue algorithms to compute eigenvalues of real symmetric matrices. So we raised the question now together with Govind and Sheehan and Tom. We raised the question whether the universality results, which I've just been speaking about, were limited to eigenvalue algorithms or whether they were present more generally in numerical computation. So we proceeded in a very extensive set of experiments with a variety of different algorithms and different kinds of algorithms. So first of all, as we were concerned with not just QR or TODA, but something like the Jacobi algorithm. And we were interested not only just in real symmetric matrices, but also with Hermitian matrices. And again, we found the same phenomenon. Once again, there was a universal histogram independent of the ensemble. Then we said, well, maybe we're moving away now from the eigenvalue problem. Well, what about solving hx equals b, where h is some positive definite matrix, and we use conjugate gradient, or more generally, where h is of a form 1 plus x, we would use GymRes. And again, we found the same phenomenon was present there. I'll say a little bit more about that later. Then we raised the issue, well, maybe this is just a phenomenon of finite dimensional numerical analysis. Maybe it's also a phenomenon just present in infinite dimensional situations. So we looked at to solve the Dirichlet problem, Laplacian mu equals 0 on some random star-shaped region with random boundary data. And again, we found, putting different kinds of stochastics on the region, we found again that the same phenomenon was present. Then we went to the idea of saying, well, all these algorithms we've been looking at are really dynamical systems, deterministic dynamical systems, and all the randomness is in the initial data. Choose a random matrix and run QR on it or something like this. But what about if we have a bona fide stochastic algorithm? In other words, you're making choices along the way. random choice. Is the phenomenon still present there? And indeed, we chose the genetic algorithm to compute the equilibrium measure for orthogonal polynomials in the line. And again, we found the phenomenon was there. The last thing we sort of took off in a different direction was a little bit different, right? We said the following: if you believe what people say, that the human brain is just a piece of hardware with some software, and if it's operating according to these rules, you should see the phenomenon in such a situation. And I'll explain how we were able to see these phenomena. So let me go on here. This is more general QR, but now conjugate gradient. So I'm sure everybody here knows what conjugate gradient is, but I'll just say very quickly, it's an iterative process where you're trying to solve wx minus b equals 0. So at any, you have an iteration. You start off with some initial guess for x0, and then you go and for x0, you compute r0, your residual, then you iterate and you get x1 and you get a residual r1 and so on. And you run the algorithm until the residual is less than epsilon, which means you've solved this problem up to an order epsilon, and the number of steps you have to take for a given random positive definite matrix W and initial and a object B, you compute the number of steps you need to achieve this accuracy epsilon. So we chose the ensembles in two different ways. So let me see if I can show you. So they're going to be two different ensembles, which I'll explain in a moment. And on the left-hand side, you're looking at conjugate gradient solving AX equals B, where the matrix size is 100 and epsilon is 10 to the minus 10. And you have two different ensembles corresponding to these two different the two different histograms correspond to these two different ensembles, which I'll explain in a moment. Now, the part of the point of displaying this, this slide is that you see there is a notion here of a scaling regime, because when n is too small, these two histograms are not really right on top of each other, but as you move into the scaling regime, the size of the matrix is bigger, these two histograms begin to lie one on top of the other. But again, you see that there is this universality there. What are the two ensembles? The one ensembles, remember, W must be a positive definite matrix. So in the one case, it's of the form XX transpose over M. X is an N by M matrix, and the entries are IID Gaussian. In the other, it's an N by M matrix, where you have Bernoulli entries. And we're looking here at the critically scaled case where M is order N plus 2 root N. This is a reasonably well-balanced situation. So that's what the critical scaling means. Later on, I'll speak about other choices of M. So the phenomenon was there in the case of conjugate gradient. Similarly, now you solve Wx equal B. But now W looks like this, 1 plus X, where X is some with IID entries or Bernoulli entries. It's a different algorithm, but again has the feature that you iterate until the residual Rx is less than epsilon. Again, you find the same phenomenon. So I'm not going to pull you through it there, but then you get to the PDEs. So what we looked at is the Laplacian U on a star-shaped region. I remind you, a star-shaped region has at least one point inside the region for which the radius can be described as a function of the angle. So that means you can specify the boundary conditions as a function of the angle. and you can choose them randomly at points, either uniformly on and around the boundary. The boundary is chosen randomly in the following way, because the radius is a periodic function of theta. You can expand it as some Fourier series, and then you can choose xj and yj uniformly. And the two ways we choose it is either uniformly in minus 1 upon 2m to plus 1 upon 2m, or as being to plus or minus these two endpoints, either uniformly on an interval or just plus or minus at the endpoints of the interval. So these are two different ensembles. Now, by potential theory, you can always convert a Dirichlet problem into a problem on the boundary, which looks like this. And so you then have to just solve this equation on the boundary, and you do that by treating this as a 1 plus x type problem, which is of the form that you can apply GMRes 2, and you solve it. And again, you find this universality coming out over here. Now, there is a very surprising situation, which is the following. So let me put it over here. Here you have 4 histograms, one on top of the other. What are these four histograms? 2 of them correspond to solving this boundary value problem. The other 2 are just plain problems where W equals 1 plus X, and this is just a purely random problem where X are uniformly distributed. So what is happening here is that the boundary value problem, you're looking at matrices in the end, which are structured with randomness in them. On the other hand, they are behaving exactly in the same way as if you're looking at a pure random situation. So the randomness just overwhelms any structure in the problem. This is very similar to what Wigner was doing right at the beginning of random matrix theory, where on the one hand, he's speaking about what happens when you fire neutrons at some big nucleus. And they wanted to know what the resonances were, and his decision was to model those resonances by the eigenvalues of a random matrix. So on the one hand, you had this big uranium atom there, which has structure, but you're treating it as a mixture of structure and randomness. Nevertheless, it behaves like a purely random problem, which is random matrix theory. So again, that phenomenon is being repeated here. Okay, so now we wanted to look at a algorithm which was not just purely a deterministic algorithm applied to random data. So we looked at the genetic algorithm, which is really an extraordinary thing. So we use it to compute the Fekete points for this function V. So I remind you from the theory of orthogonal polynomials that if you minimize this and you obtain the minimizers of the Fekete points, then for any n, you get the Fekete points, you compute the counting measure, the Fekete points, that converges the equilibrium measure for the orthogonal polynomials. And so we wanted to see, can we compute effectively the equilibrium measure? So how does this genetic algorithm work? It's really a wonder. It's really extraordinary. It has 2 components, mutation and crossover. So how does it work? So you fix a distribution D, and we're going to show universality with respect to this distribution D. So you draw an initial population of endpoints. This should be, I should say, an initial population of little n equals 100 vectors. So it's P1 up to P. Each one of these is a vector consisting of capital N points. So remember here, capital N is this variable over here. So this is your state at time t, say. How do you go from this particular state to the next state? Remember, you've got 100 choices here, and you're picking the one from these 100, which is minimizing your functional. So you proceed in the following way. You flip a coin and you're going to do either mutation or crossover, one or the other. Mutation works in the following way. You pick one of these individuals. So suppose you pick P1. It has capital N entries over here. Then you pick two numbers, little n1 and little n2, from 1 up to n, and you draw little n1 numbers from your distribution D, and you use these numbers to perturb the entries in your chosen P by just adding these numbers to it. And then you'll get a new vector of size capital N, which you call P1. Then you choose n minus n2 numbers from D, and you use them to perturb the last n minus n2 entries of P. That will give you a second P2. Finally, you do the same thing with the numbers between these two n's. That means out of your given P, you construct 3 additional elements P. So you've now got, after mutation, you've got a 103 vectors, each of size n. For crossover, you pick 2 entries, 2 rows. Let me go back. Maybe you pick P1 and P2. Then what you do is you pick 2 numbers, n1 and n2 from here, and you replace inside P, you replace the n1th element of P with the n2th element of Q. That gives you another P, and you do the opposite for Q. So at each step, you flipped, either you're going to do crossover or you're going to do mutation. The new individuals are appended to P. So after mutation, you now have your original P plus another 3 vectors of size capital N. Or after crossover, you have 102 entries. And your update from P to P prime is simply by choosing from these either 103 or 102, the 100 PIs, which have yield the smallest values of HP. Now, this extraordinary algorithm actually converges. It's unbelievable, but it really does. And we looked at 2 particular potentials, V equals x squared, giving you GOE, right? Or this particular potential, and the difference between these 2, you remember, this has a support on 1 interval, this gives rise to an equilibrium measure support on 1 interval, this has support on two intervals. And again, so the top here is for V equals x squared. The size of these vectors, there were 100 vectors, they each of size 40. Well, initially of size 10, and this is of size 40. And again, the universality is with respect to the choice of D. So you have 2 histograms here. One is uniform on this interval, and the other is just the endpoints, either uniform or Bernoulli. And again, you see they lie one on top of the other, and you see the universality present there again. This is now in the case where Vx equals x squared, 4x, of course, minus 3x squared. And again, the universality is present there. Okay, so then we came to the point where we had this idea, well, if you believe that the human brain is just a big computer with software and hardware, then the phenomenon should be present there. Well, now it's not so easy to say I'm going to do experiments on people, right? It's not so easy, but fortunately, this didn't bother my colleague Bachten, and he worked with a psychologist at Minnesota, and they got 45 participants, volunteers. And each of these 45 participants was shown 200 pairs of images. So each one of these 45 people was shown 200 pictures looking like this. So each picture has a block of dots on the left and a block of dots on the right. And what they had to do is to guess which one has the larger total area, left or right. And then, so each person has to make 200 choices. And what is recorded is not whether they got the answer right or wrong, but how long it took them to make a decision. So each person is producing 200 numbers from which you can build a histogram. And what you find is that they're all coming out with the same histogram. You can see it over here. This is person 16, 21, and as we're dealing with such low numbers, it's quite remarkable that you're getting this kind of result. Then my colleague Bachtin, together with his friend, devised a model. It's called Glauber dynamics on a hypercube, and you can see what the basic idea is. Your state vector is a vector of size capital N. For each entry, it's either plus or minus 1. And given a spin flip intensity, that will tell you when you can make a change, what time you need to make a change. And you get that using the spin flip intensity. And the idea is kind of cute, right? You run the algorithm, you got a desired accuracy, say a half. You start off, say, with all of these x's equal to 0. Well then, so x1 is 0. So in your mind is this, right? You say, I think the left has more volume. No, I think the right has more. And you go back and forth and back and forth. And so x1, you say no. x2, you say yes. And so you add these all up until you reach a decision, which means that the sum must be bigger than something, maybe bigger than R. So they compute this model for a given choice of CIs, and they come up with a distribution, which is this distribution, this hard line here. What we did is to show that for different choices of these CIs, you have universality. It wasn't that they were able to just pick the right CI which was given you. In fact, you had universality here for your distribution of the CIs, and we verified that. Okay, so let me just move on a little bit. There are many other cases. Now, we came to the point where we had to stop pretending we were applied mathematicians, and we had to remember that we were actual mathematicians, right? We had to see if we could actually prove any of these things. So we had to take one of these algorithms and really prove that this universality was present. So we chose the following problem. We took the total lattice again, and our stopping time was the sum of the squares of the elements in the first row off the diagonal, x1, 2, x1, 3, and so on, summed up. So when this is small, it means that you are deflating around the 1, 1 entry. It means your matrix has a 1, 1 entry, which is non-zero, but everything else in the first row and first column is 0. And what the 1, 1 entry should be the eigenvalue of the matrix to an accuracy epsilon. So that's our stopping time when this quantity is less than the epsilon. Then we analyzed the flow, and we found the following, that you need to know that this distribution exists. This is a result in random matrix theory. And let me say that this work was done about four or so years ago, and we could not have done the analysis without the most up-to-date information from random matrix theory at that time. So it really relied on information. So here is the distribution, the inverse of the gap between the top and the next eigenvalue. This has a limit as n gets large, and this distribution, the inverse gap distribution, appropriately scaled, exists and is universal in random matrix theory. And this is our result. So we look at very general ensembles, very general invariant ensembles, either real or Hermitian or Wigner ensembles. And we look at the scaling regime. Log epsilon inverse upon log n should be bigger than some number sigma, which is bigger than 5/3. Then the time it takes you to compute the top eigenvalue, scaled in this particular way, converges as n gets large to this universal limit, which is just what it's telling you is that the convergence time to compute the top eigenvalue is governed by the distribution of the difference, the inverse of the difference between the two top eigenvalues. So here's a theorem demonstrating universality. And you compute the expected time, and you see that the expected time grows like n to the 2/3 log n. Now, what is different here from a lot of the analysis from a lot of numerical analysis, a lot of numerical analysis faces the issue that there are exceptional events which can make you get bounds which are much too big. Those events, unless you're doing some kind of smooth analytical approach, those kind of events are going to give you bounds which are just much too big. Nevertheless, these bounds over here are exactly what actually happens. As you can see here, we're using 250,000 samples, n is 500, epsilon is 10 to the minus 4. And this is the distribution for the real scale halting times actually observed compared against this curve over here. So you should observe. So why do we actually see this in our actual, how do we know we're in the right scaling regime? Well, I think people would agree that epsilon equals 10 to the minus 16 is a pretty standard accuracy. And n less than 10 to the 9 is a reasonably sized problem. And if you plug that in over here, you'll get 16/9, which is bigger than 5/3. So practically, in most cases, you're going to find yourself in the scaling regime. So similar theorems have since been proved about QQR and other situations. There is a numerical theorem which says the same is true for QQR with shifts, but we haven't computed the, So I'm not going to go through the proof now, but I want to speak about a little bit about some further rigorous results. So if you go back to the conjugate gradient, and we look in the situation where the matrices are n by m, but instead of being in this critically scaled region, you say that m over n is equal to 1 over d, where d is less than 1. So m is strictly bigger than n. This is a well-conditioned matrix. And you can show that as n gets large, the residual after k steps in L2 with respect to the distribution converges to a deterministic limit. So this is one of these surprises. It's telling you that you give me an epsilon, I then choose k, so the d to the k over 2 is equal to epsilon or close epsilon. You see that it's telling you that the conjugate gradient algorithm is essentially deterministic. You just need to take that many steps, and no matter what your distribution is, you're pretty sure that you are going to achieve your given accuracy. In later results, Elliot, together with Tom, showed that not only does this RK converge to D and L2, in fact, this distribution is in fact Gaussian. Then in later work, which with Ding and Tom Troglin, which Ding will speak about later, they generalize. So I won't say more about it. Ding will explain more about it. So I just want to spend my last 3 or 4 minutes to try to describe what the takeaways are. Is there? No. Okay. So the first one is there is a signature. So this is really the real result. It's telling you that if you take, and it's this whole entry into the mystery of very large dimension, you're getting into this ray where all remarkable things begin to happen, is that if you get into a large enough region, something universal is going to happen. And that universality is going to be expressed in this particular case by existence of a signature, and the signature being the histogram. The histogram is the signature. So, and the claim that we will make is that if you have a dynamical process and you apply to in a random context, then provided the dimension and the accuracy, etc., are in the right region, you're going to see a signature coming up. Now, it's really telling you that the quantity you're going to get, let's call it xn, will look like A plus B plus something universal. You take away that. These are the two components but everything here is all that's important are these two things. Now, this should put you in mind, and maybe people won't like what I'm going to say now, but I'm going to say it, is that if you've got an integrable Hamiltonian system, you want to find variables x so that this looks like A plus BT. In other words, you want to linearize the flow. Now, you might think that this is not a very good analogy to do. But if you want to see why it's actually a better analogy than you might initially think, ask yourself, what is time actually? Time is a universal concept. Do you mean the number of swings on a pendulum? Or do you mean the number of firings in an atomic clock? Or do you mean the number of heartbeats, as Galilei should do? There is a universal object called time. And that you can record in different ways, but nevertheless, it's time itself is really a universal object. So it is in this sense that computation in this form is an integrable system of this kind. Maybe people are not happy with this analogy, but I'll leave it like that. The next thing over here is that these ideas can make themselves felt in non-destructive testing. I mean, the most famous historical example, right, was with Archimedes, right? The king gave him some gold and told him to make a crown, and the king was suspicious. How did he know that they didn't put some metal in there, some other metal in there? And how is he going to find out? Without destroying the crown. You want to do it, and then, of course, Archimedes' principle was supposedly came out of this. So what you could be in the following situation, you buy some software to do something, maybe an eigenvalue package. They give you a disk, but they don't tell you what is in that disk. You can't open the disk up. But what you can do is you can run it on random data. And if you get coming out the histogram for QR, you know that they're using some QR-based thing. Or if it comes out looking like Toda, you know that's what you're doing, or Jacobi. So it can be used in that way. A different way you can use it is you go into a supermarket with a pen, paper, and you just watch what is happening at the checkout counter. You see people putting in their card, and what you record is how long it took them to get an answer. From that, you can infer back something about the statistics about the security system which is being used there. Is it this kind or that kind? Now, the issue here is, how do you enter? How do you do the Alice in Wonderland thing? How do you get into this world of large numbers where real universal phenomena begin to occur? Your entry point, you remember Alice had this drink me, little bottle which said drink me, and it got bigger or smaller. And what you do is you need to use a dynamical process. It's the dynamical process which will bring you in there. This is, of course, very familiar in many different ways. For example, how does one prove universality for Wigner matrices? You run a process, Dyson-Brownian motion. It's that process which brings you into the universal world, and exactly the same thing here. You have a dynamical process which feels out the environment. The final takeaway is that if you have your favorite algorithm, and I'm sure everybody has their final algorithm, take your algorithm, apply it to random data, run it until you achieve your desired accuracy, and see whether you have a histogram. My bet is that you will surely get one. Okay, thank you very much.